In this, we're just kind of keep moving with our orbits 101. So if you remember right, we left off with a two-body equation of motion. So r double dot is equal to negative mu over r squared times position vector, or our unit vector, to their position vector over its magnitude. I'll have a separate video showing how to solve this two-body equation of motion. But when you solve it, you end up with r, just the magnitude r, as a function of nu, and now nu is our true anomaly, and that is the angle of the position vector with respect to the periapsis. And we'll draw a nice, and we'll put Earth here. We'll say this is RP, this is RA, so our periapsis and our apoapsis, which makes this our major axis, and let's say this is a halfway point. So this is A, our semi-major axis. And let's just go ahead and draw spacecraft here. So this is R, this angle is nu, the Greek letter nu, N-U. All right, so solving this two-body equation of motion, we get R as a function of nu times A, our semi-major axis, times 1 minus e squared over 1 plus e cosine of nu. Now e is our orbit's eccentricity. The eccentricity describes how elliptical the orbit is, or what type of conic section it's going to look like. And we'll talk more about conic sections in the next video. So we can define E in a more mathematical form. E is equal to RA, so the radius of our apoapsis, minus RP, all over RA plus RP. And then we can also define our semi-major axis from the apoapsis and the periapsis. So A is equal to RA plus RP, which is just the entire major axis, divided by 2. Easy. And actually, I don't think I explained what the apoapsis and periapsis were in the last lesson. So the apoapsis is the furthest point from the body you're orbiting, and the periapsis is the closest point. For Earth, that would be the apogee and the perigee. Apoapsis and periapsis. I believe these words are worded in the Greek language, but I'm not totally sure. All right, so I think that will just about cover it for today.